Hi, everybody. Welcome to Byte Ventures, where we deep dive into the marvels of technology. Today is a very special episode where we deep dive into a white paper, which is a scaling Memcache at Facebook. So, it's a very insightful article. It has explained very beautifully the different kind of intricacies that we face while scaling a single machine to clusters across the globe. So stay till the end, you'll have a lot of fun to know a different kind of interesting insights about the Memcache and the deployments. Without further ado, let's dive deep in. So let's give a first basic overview of things. So as you might know or might not, Memcached is a single machine in-memory hash table. That means it's a single machine, the key value store, you give a key, you give a value, it stores in the memory. Facebook wanted to build a distributed key value store based out of the Memcached open source system, right? And that is what the whole paper describes, how they went from a single machine to all the world. And their requirement was, because they were kind of like very hyperscale system, they wanted to make a distributed system that could process up to 1 billion queries per second, QPSs queries per second, and can store around trillions of items at a single point of time. So this was the basic criteria of what they wanted to build at the end of this paper. So let's talk about some initial considerations. So initial considerations were the users on the social networking site consumed more than they create. So the system was a read heavy system and the alternate is a write heavy system, which is not in this case. The read fetches from multiple data sources because they have data sources as backend like database, MySQL database, Hadoop file system, HDFS, or backend services, or third-party APIs and stuff like that. So they wanted to build the distributed key value store with a hybrid caching strategy. And for that reason, they have built this whole thing. Okay, there's a primary difference between the Memcached with a D and Memcache without a D. So when they refer, or when I will refer to Memcached in this whole video, it will be referring to a single binary or the source code, right? And when we are referring to Memcache, it will be referring to the distributed system that Facebook built, right? If you remember the topic, it's scaling Memcache at Facebook, not Memcached at Facebook, right? That is the primary difference. You just keep in mind. I'll constantly remind in the duration of the video. Okay, the primary thing. So Memcache deployed in a single box, right? So how things were, what are the requirements for a single box, why they need it in the first place, and how did they go it from there? Okay, so if you think about it, Memcache is kind of an in-memory hash table, which they used for two different purposes. One of them is a general cache, one of them is a query cache. So what exactly is general cache? So general cache is kind of like a normal cache which each developer might use, store for the different configurations that they are using. Or if they have a machine learning model, they want to store some value and reuse at the computation time, they can store it in the general cache. So the general cache was used for this purpose, and they wanted to leverage Memcache for this exact use case. The second primary use case was the query cache. So whenever they wanted to query a database, they want the Memcache to help them reduce the load on the database, because there are like thousands of web servers or thousands of users concurrently accessing their site. If everyone starts making requests in real time to the database might get killed because of the overwhelming number of requests that it receives. So they wanted to have some kind of protection layer to the database or the persistent storage. So let's talk about the query cache. So think about this. So this is the web server that we are talking about. This is the Memcache, and this is the database. So as usual, if you are a computer science student, you might be thinking that, okay, cache is a helper to the database. So whenever there is a request that comes in, we want the request to be served as soon as possible. And for that reason, we have a cache. So that is why whenever there is a request from a web server to access any specific key, it goes first to the cache instead of the database, because that is generally faster, and that is the whole purpose of using cache. So the step one, whenever there is a request for K, it goes to the Memcache system. If it gets it, well and good, the request is served. But if it doesn't get it, then it fires the same query to the database, And whenever it gets back the response, it sets the value in the cache itself, so that whenever subsequent request comes in, they don't face any value of going again to the database, right? That is what the whole purpose is. When they have a write system, so here is the web server, the writing doesn't happen to the cache because cache is not authoritative source of data or the truthful source of data, because it's kind of like a derived field from the database. So whenever someone writes, they will make sure that they write it to the database. But think about this. As this is not an authoritative source of the data, we can file a delete query, and whenever there is a subsequent request that is coming in, it'll go to the step one. Like, it'll not get it, there'll be cache miss, and then it'll fetch from the database and set it. So it'll be a lot hassle-free in that case. And that is why you see the delete key functionality here, because the delete also is an idempotent request. If there are like multiple deletes, what do you mean by idempotent? It's like if there are multiple deletes, there's no change in the system that is happening. Okay, so that kind of makes the distributed system very simple right from the beginning. Okay, let's move to a little bit more. Okay, so why do we need a cluster? So think about this. Facebook has a huge scale, right? So if you give all of the load to a single box or a single computer, that might get overwhelmed, right? So what Facebook did is like they distributed the keys or the values that are stored in the cache across multiple Memcached servers, or which we call as a cluster. Okay, so in this case, the primary concern was to get minimal latency from the cache, right? That was the first concern. And the second concern was to reduce the load on the database, because as they have now multiple cache servers, if any of them fails, the request fall back to the database. So it should not happen that the database is overwhelmed because of a lot of cache misses, right? These were the primary concerns they wanted to take care while deploying for a single cluster. Okay, interesting. So let's talk about how do we reduce latency. Okay, think about this. So when we have a huge load, we distributed the data across different Memcache servers. So now you'll think about, how do I reach to that location? How do I know which server has the key? So this is a problem of load balancing. If you have come across load balancing, or LBs in this case, which sits in front of a multiple servers, which decides where to go, it's a very defined, deterministic, solved problem. So I'll not go into much details of what exactly is load balancing, what is consistent hashing. I will attach some resources in the description if you are not comfortable with the topic, but just think it as an abstract topic now, that there is a way I can get to a right server given the key, and that is used with the help of consistent hashing. So consistent hashing is a way to reach to a kind of server when we have multiple servers, depending on the requirement. Awesome. So if you think about this, we have divided kind of like this. So we have a web server here, and we have multiple Memcached servers. So the round represents Memcached servers, and the square box represents a web server. I will name this Memcached servers. So for each of the requests, it can happen that as the keys are distributed now, this is reaching to this is reaching to this is reaching to this, and this is reaching to this. Let's assume that to serve a single request, the web server has to reach out to all of this Memcached server that are present, right? What will happen? So this is basically a one-to-n request in a single request as well. If you take a little bit of more time, this will go on for other web servers as well. And eventually we'll reach a state where each of these web servers is reaching each of this Memcached cluster. So it's like all to all request relationship thing, right? And that is what is a big problem, because when all web servers are reaching all Memcached servers, it's a huge problem, because if one of the Memcache server is down, all the web servers are impacted. All the web servers now request to the database in turn, which in turn overwhelms the whole web, the database, and that gets a lot of confusion, because now that is leading to cost congestions, lot of overloaded clusters, the performance is degraded, and a lot more cascading failures. So we'll talk about in cost congestion in a while. What did they do? So they wanted to not allow talking of the Memcached servers to one another. right? So if you go back to this diagram, oh, I removed the diagram. So there was, we're talking about from web server to a Memcached server, right? So if we allow the Memcached server to talk to each other, then when we send the request to one of the Memcached server, that will be giving us all the values that we need for that whole request. But think about this, that'll create huge mess, because now we're thinking about making stateful servers, and that is very bad, and not very bad, I would say, but it'll be very difficult and challenging to maintain, challenging to scale, challenge to deploy and stuff. So they wanted to keep all the complex logic on the stateless Memcache client. Okay, now what exactly is Memcache client? So Memcache client is something that sits inside each web server. So this is the web server, this is the Memcache client. Sorry for my handwriting, but yeah, understand it. So each Memcache client has given a lot of responsibilities to talk to the Memcache servers. So it's basically an interface between the web servers and the Memcache servers, and it handles a lot of things. So like it handles a serialization or compression of the request, it routes the request, it handles the error, it batches the request, and so on and so forth. And the Memcache client maintains a list of available clusters through various configurations. We'll not go into much details of that, but think of it as there is a list which gets updated and which signifies what are the available active clusters that can be reached and that can be performing as well. Okay, so instead of keeping the complexity in server to server communication, they took out that whole complexity into the Memcache client, keeping it stateless. Okay, so what are the other optimizations they did in this process to make sure that they reduce the latency, right? So instead of having a single request, because as we talked about that, a single request need to talk to multiple Memcached servers. Suppose, let's say we have 4 keys that we need to fetch from the cache, right? It can happen that we are making serially 4 serial calls and D, right? And it can happen that A and C could have been fetched at the same time. That is what the first optimization talks about. The first optimization is parallel request and batching. So we'll try to reduce the number of round trip time, or RTT, we say it, we make to the backend service or the cache in this case, so that we fetch the data in the least amount of calls made to the cache, right? So each page, as we talked about, requires multiple keys. So based out of that, we create a DAG. So DAG is a directed acyclic graph. It's kind of a dependency tree. So like what needs what. For example, if you're fetching A, B, C, D, as we last did, and for example, C needs A to be present, but B need not have any prior dependency, and similar is D. That means A, B, and D can be fetched at one go, and once the response comes back, we can use the A's value to make a request to get the C. Based on this, they can decide that, okay, which all things can be clubbed together and passed as a single concurrent request. Then a batch request is fired. So as per the stats they did, so each batch request was averaging almost to 24 keys per request. That was a huge improvement of just going through a single key per request to have around 24 keys per request. So parallel request and batching helped them reduce the latency to a lot more extent. Okay, let's talk about the second thing that they did to reduce the latency, because we are trying to reduce the latency in a cluster. So they tweaked the kind of the client server communication. So we talked a little bit about improving the Memcache client or making it more complex instead of making the server to server communication. So let's talk a little bit in depth about that. Okay, that's interesting now. So when they were developing the Memcache client, they provided 2 variants of the development or the client. So first is a library to be embedded into the application. So any application can embed a Memcache client library as is and uses it as dependency. Or the second is a standalone proxy named MC router. So this is a very interesting thing. They kind of separated it into a proxy, which is kind of a Memcached server interface. As I was talking about, this Memcached client can act as an interface to the Memcache server. So whenever someone wants to reach to a X Memcached server, they can go through this MC router proxy. Okay, some more cases. As it is a network communication, because we are reaching from one place to another, because web server is in a different box, a Memcache server is in a different box, we are doing network communication. So there are two kinds of network communication, which is UDP and TCP. I think you might know the difference. So yeah, I'll attach some documents regarding this in the description as well. Okay, so for getting the cache value, which is like, we don't mind if we lose that, but that don't happen. But yeah, we don't want 100% availability in this case, like when we update things or when we delete things. So it's okay. So that is why we used UDP, because UDP is less reliable than TCP. So what did this do is, like, whenever we fired a GET request, this request didn't have to go through the MC router proxy. It can directly bypass that and reach a particular server. And that helped in reducing latency and overhead, because it doesn't have to make a connection, doesn't have to store the connections and all stuff that TCP does, and give out response back to the client, right? So there will be obvious cases of package drops in the middle or out of sequence response, but client terminated them as errors or cache miss. But as it was already requesting the backend services or the database, the cache was not updated. That means those requests didn't fire another request to the database to find the actual value. So it was no insert operation to the cache, right? Though there was a cache miss, there was no insert in the cache. Keep this in mind. The second thing were the more reliable operations, which we call the set and the relay operations. Those were performed via the TCP route because they were more reliable, and we didn't have to employ a retry mechanism to make sure that those things get set properly in the database, right? So these were the kind of some tweaks that they did to improve the performance or the reduce the latency in this case. When they talked about TCP connection coalescing, that means they're merging multiple connections into one, and they did see some improvement in latency in that case as well. But when they talked about UDP gives about around 20% reduction in latency than in TCP. So that is how they got around to have finer latency metrics in this case. Okay, let's talk about optimization 3, or handling the incast congestion. What is incast congestion? First, we'll talk about that. So incast congestion is a many to one problem. That means there are situations where you have multiple things at one place and they're talking to one single point at one point of time. That means, let's say this is communicating. These are 4 servers on the left hand side, and they're communicating to one server on the right hand side. That means if the client in this case is talking to multiple memcached servers and they send out the response almost instantly, then the switches and the racks that is present through which it is getting the values will get overwhelmed, because there's all the responses are coming at the same time. And that is what the incast congestion problem is. Like all of this getting through at a single point, almost around a single time. So how do we solve it? So we might have learned about in data structure a thing called sliding window. So for example, if we are given an array and we want to find a sum of 3 elements and has to go on and so on. So what we did is, like, we took a sliding window and slided that whole window across and just took one element here, one element there, and that is kind of the same concept. So sliding window mechanism is used to control the number of outward requests that is going from the Memcache client. And it's very interesting to see some of the things. So when the Memcache client received the response, it can either be success or a failure. In case of success, we can say that we can increase the window, not like the thing we discussed about array. There was a fixed thing, but we can of course use a dynamic changing sliding window. But in this case, the successful response meant that the Memcache servers are able to process it, or the client is able to handle those response. It can increase that. And then the sliding window size is increased. And in case of failures, you can see that, okay, the clusters are probably sending too much response. The client is not able to handle. It will reduce the size of the sliding window to make sense the system performs at its optimal performance, right? Okay, let's see a diagram. So as the window size increases, this is a very common thing, because at smaller window sizes, it's kind of like serial execution. So this graph represents the milliseconds of wait time. So the web request had to wait for this amount of time before getting processed, right? So if the window size is pretty small, or 100 is the unit size, 100 units, then they had to wait a lot, because after response comes back, the next window goes in. As the window size increased, the response, the waiting time, I would say, decreased a lot, because from around 45 to 50 milliseconds, it dropped to around 8 or 9 milliseconds just by doubling the window size. And then further doubling, it did come across to a decrease as well. But as soon as we increase the number of the size of the window in this case, you see strangely that the wait time increases. Think about this. Why would this happen? This would happen because now at 400 window size, the client is probably facing in-cast congestions. And that is how it'll decide that, okay, now I have to reduce the window size and keep around this length. And that is when the system will perform at its optimal performance, and everyone will be happy. And the latency will be down. The system will be at its top-notch performance. And yes, that is it. Okay. And yeah, there is one thing. The Memcache request, irrespective of its destination, is put into a single window. The request is going to, let's say, Memcache server A or B or C or D. It doesn't matter. It has to be a window 4. Then all of them sit together, right? That is how it is defined. Okay. So now we discussed about reducing latency. The first is parallel request and batching. The second was tweaking the client server communication using UDP in certain cases, not switching to stateful server to server communication. Rather, all of the logic goes inside the Memcache client. In the third, we talked about handling in-cast congestion using sliding window, right? Okay. Now we talk about the next problem in a cluster. So now we're talking about the cluster. So let's talk about reducing load. So reducing load is an important problem if there is a cache miss that is happening. So when the desired data is not available in the cache, the fallback is the DB or the backend services. So in case there is a lot of cache misses, we should take care that there is no additional request to the database, which is already overwhelmed. Okay, let's talk about the first optimization to reduce the load. Okay, so the first optimization is a method or the mechanism called a lease mechanism. So let's see what exactly is the lease mechanism. So there are two ways, or let's talk about the first way, which is called the stale sets. These are the condition due to which the load on the database or the backend services might increase. So the servers are expecting a recent value, and the cache is not able to provide the latest value to them. So they are trying to reach out to the database to fetch the latest value. So even if there is data in the cache, but the cache data is stale, and that is what defines the stale sets. And it can happen that due to invalid sequencing, because of this, there's a huge load on the backend services, because the web server is not happy with the content of the Memcache servers, right? And the second problem is the thundering herd. So what exactly is a thundering herd? So when a key undergoes heavy read and write, if you remember the first diagram, every write in the database deletes the key, right? That means if any of the read requests happen during that time, they have to go to the database. That means if there are huge number of writes into that database and the reads, there'll be a lot of default reads. That means a lot of cache misses in that case. And that will lead to a huge load on the backend system. So what can we do to solve this problem? And that is where the lease comes into the picture. Or in other words, we can say that the Memcache instances gives a lease to the client to set the data back in case of the cache miss. Because once the cache miss, it'll fetch the database, it'll fetch the value from the database, it'll try to set it to the cache, right? Client provides the lease token to set the value to the cache, and the cache will determine that whether there is any further changes that has been done after the token has been given. Okay, still confused? Let's talk through the diagram. Okay, so let's say client 1 asked for a key k to this cache, right? So let's say this is a Memcache instance or a Memcache server. So there was a cache miss, it given a token tk1, which is a function of the key that is given to this. Similarly, it tried to go forward and connect to the database to see that, okay, give me the value of k now, right? Meanwhile, client 2 comes in and checks for the data k, and still it'll face another cache miss, and that is why when it'll consider that, okay, it'll give back tk2 because it'll try to fetch it from the database. It will now go fetch the k key from the database and come back. Think about this, right? This is still stuck for some reason, and this came back, and this set the value. So now the cache is having a value of kv, let's say, right? When it will come back, it'll try to set the value. So what it will say that, okay, I have the token tk1, and this is the value for the key that they have, which is k in this case. Please set the value v in this case. But what the cache will say that, okay, tk1 is not the latest thing because the latest one is tk2, because I have given the token to client 2 which came later and I still have it. So it will reject the operation of tk1. And that is how the lease mechanism helps us solve the stale data or out of order sequenced data in this case. Pretty interesting, right? Okay, let's move forward to optimization 1, but in this case, handling the thundering hard problems. So thundering hard problems were like, there are a lot of writes and a lot of reads to this, and that leads to removal of data before being used by the read clients, right? So what they did in this case was register the rate at which it returned token, because as we have talked in the last optimization, that leases are sent out by the Memcache instance itself, right? The client requests the Memcache servers, Memcache returns a token to use it to set back the data when it gets back from the database, right? So we can limit the rate at which the tokens are generated. That means in this case, or in the default case, they're configured to return token once in 10 seconds for a key. For a given key, only one token will be generated per 10 seconds. So what happens? How does it solve? So if a client requests token for the same key within those 10 seconds, it will be signaled to wait for some time. That means it will not be directly given another token, or it will not be failed, but there will be a special signal signaling that it has to wait for some time. And then, as we're assuming that the write latency will be pretty small, in this case, someone would have written the data to the cache, and whenever this client makes a call again, that, okay, I want a token now, or that means I want the value of this key to the Memcache server, the Memcache instance, it will be a cache hit in this case. And that solves the problem, because with a little wait, or probably a couple of seconds of wait, we reduced the load on the database. So there was a comparison study that was done at Facebook. So without any lease, the peak rate of the DB or the database was 17,000 queries per second. So it was reaching around 17,000, but with lease in place, it was reaching around 1.3K QPS. Huge performance improvement to reduce the load on the database. So that is how lease or lease mechanism is used to reduce the load that is reaching the database at the end. Okay, and the application can reduce the wait times. So what can it happen that you might see that certain things were deleted, so they had to wait for like 10 seconds in this case, right? So what they can do is like they can maintain an auxiliary data structure to hold the recently deleted data. So in case the data is deleted, they can check the auxiliary data structure, which probably gets deleted in shorter time, but they might have some chance to reduce the wait times. Okay, and that is just one of the optimization that they did to improve or to reduce the load received on the backend systems. Okay, let's talk about optimization 2. We talked about the first optimization is the lease mechanism. The second is the Memcache pools. So what exactly is Memcache pools? So, oh, there's a typo. Okay, never mind. So using Memcache as a general purpose cache requires sharing this infra with different access patterns or different memory footprints or different quality of service requirements. For example, let's say there are 3 services which are using this cache as a general purpose cache, and they have very different access patterns and very different memory footprints. What can happen is that it creates a negative inferences because one is setting values which are highly frequently accessed and one is setting values which are not frequently accessed, and it will lead to mismatch because one will override the other, which might be used in the next instant, or someone is not overriding things which are not frequently used. It's kind of that situation, right? So to solve this, a cluster's Memcache server is distributed into different kind of pools. So each pool has a very specific functionality. So the default one is the wildcard, where the default goes in, and they can have different pools based on the requirements. For example, a small pool stores frequently accessed keys, but the miss is inexpensive. That means if it's missed, doesn't matter. Fetching it from the database isn't that a costly operation. And there is a large pool, and that is why the size of this pool is smaller, because the miss is inexpensive. Even if that is missed, no problem, we'll fetch it again and store it into the cache. And there is this larger pool because in this case the miss is expensive, but they're accessed less frequently. So we don't want them to be replaced, and that is why the size of the cache in this case is a little bit bigger. Okay, that is how having a Memcached pool reduces the load on the database, because now that we have optimized the different categories of the cache, we don't need to reach out to the database as often as we would without the description of these pools. Because if you're using it as general cache, general purpose cache, then the negative interference would have revoked some of the items that we might need, right? The third optimization strategy is the replication within pools. So now we talked about having different pools inside the cluster. Now, how do we replicate the data inside pools? So why is this needed in the first place? That is the first question that we should think about, right? So the pools get more requests than others. So it can happen that certain pools are very hot. That means they're getting more and more requests than the other pools. And this is leading to bottlenecks of the Memcache server, because it's eventually a server, right? It can process to a limited amount of requests per second. So if it's being overwhelmed by a lot of requests, that is a big problem because it's affecting the whole performance. So we need to replicate within pool so that we have reduced the load on the database. So application fetches many keys. So there are certain requirements for this condition, because this is an optimization which cannot be applied everywhere. So what if the cache sizes are so big that we cannot like replicate things? This can be imitated in a situation where the entire data set fits in 1 or 2 Memcache servers, and the application fetches many keys simultaneously and so on. And the request rate is much higher, where a single server can't handle that. So, okay, let's talk about why do we need replication? Some of you might be thinking that we could split, right? So if a single Memcache server had like 100 keys, probably we would make 2 Memcache servers with 50 keys each, and that would eventually solve the problem, right? Well, not exactly. Okay, let's think about this. So we have the server processing 500,000 QPS or RPS, whatever you say, right? That means Each second, we are receiving 500,000 requests per second. We want to scale our system to serve around 1 million queries per second. So when we have 500,000 QPS, what is the problem? Let's talk about the case 1 here, case 2 here. So case 1 is split. That means let's assume our Memcache instance had 100 keys and the web servers were trying to fetch those 100 keys. So in this split case, what we'll do is we'll make 2 Memcache servers with 50 keys each. And this is replication, where we have 2 Memcache servers with 100 keys each. What is the performance difference that we get? Okay, so in this case, we have 500,000 RPS. So now if we scale that to 1 million QPS, what will happen is that even if the keys are distributed, each request will have to go to both of this, right? Because we don't know which all keys are here, which all keys are here. Even if we distribute randomly, then we'll say that 1 million QPS would go here, 1 million QPS would go here, because they need to fetch all of the things that are associated with each request. But in this case, what we can do is we can divide that 1 million QPS into 500K and 500K QPS, right? And as both of them contain the whole data, each one of them can serve it. So that is how we scale our whole system by replicating the 100 into 2 instances. We can say that now we can handle a peak load of 1 million QPS. But even if here, we still can't say that because our servers, let's say, only accept 500K QPS. That is it. So even if we want to scale it to 1 million QPS, each server in this case had to serve 1 million QPS to make sure that we eventually get a 1 million QPS, which is not the case. And that is why we go with the method of replication in this case. I hope that makes sense. Okay, let's move on. If you have any questions, please let me know in the comment section. I will go on, attach some documents in the description. Okay, let's move on to this. So now that we have talked about reducing latency, reducing load, and let's talk about handling failures. How do we handle failures in this case? The cache mesh leads to extra load on the backend, which leads to the cascading failures. So it can happen that there are two kinds of failures in this case. One is a small failures, or where the certain percentages of the node are inaccessible and stuff like that. In the second case, a widespread outage affecting a significant number of Memcache servers within the cluster. So we have to deal with these failures in a very different way. So for smaller failures, we can have automatic remediation system, that is, it'll taken care of automatically and stuff. And then for the larger outages, we can say that the cluster is taken offline and the traffic is diverted to other clusters. So in that case, it will be helpful for us to say that, okay, we have remediated it because the cache is failed. We are diverting the whole traffic to another cache, will not impact the load on the database or the backend service. There's a very interesting thing in Gutter as well. So there is this Gutter, or a small set of machines in a cluster responsible for handling the failures. So in case certain boxes go down or certain cache boxes go down, this Gutter will be acting as a cache which can take on some additional loads. So how does they work? So in case of the cache miss, the request goes to the Gutter pool. If miss, then we fetch it from the database and set it in the Gutter pool. So the principle is that even if the Gutter pool will have some stale data, it will give us some protection from overwhelming the backend clusters that we have. So that will be the primary concern that we'll be fighting for, right? Even if there is a little bit of stale data, it doesn't matter. It'll go on to achieve the eventual consistency in certain time. Okay, so that was all about clusters. So now we talked about cluster. Let's talk a little bit further than a cluster. So what if we have a single region or multiple clusters that need to have the support for the Memcache deployment, right? So replication is emphasized because in a single region, replication is of a primary concern. How do we solve it? How do we decide what are the problems? and why something is working, why something is not, let's dive deep in and think about that. Okay, adding more web servers or more Memcached servers would eventually solve the problem. But if you think about it, it will not. For example, a viral reel or a viral video, if given more resources, that will go more viral. It will not be of the situation that, okay, more resources are added now, it will not overwhelm the backend clusters. It'll actually go worse. So let's talk about this. So I hope you can see this. So this is the whole region. Ignore the master word here. Now, when we have talking about regions, region consists of multiple clusters. So think about this. So each rounded rectangle you see is a front-end cluster. Each front-end cluster has multiple web servers in it, has multiple Memcache servers in it. And each of these clusters are tied together to have multiple different front-end clusters. And a storage cluster, or the actual database, is shared across all the front-end clusters. And this whole thing is termed as a region. Okay, it means we have multiple web servers, multiple Memcache servers in a single cluster, and a single storage cluster in a single region. And that is how the definition of region goes like. So replication is used in this case because independent failures in this case. And obviously there'll be less incast ingestions, less incast congestions. I talked about ingestion. So less incast congestions, and it'll be having tractable network configurations. So that is how the replication gives the leverage for. So the storage clusters, they are the authoritative copy that we discussed. As in the first slide, the database is the authoritative copy, and the cache is kind of like deriving the values from the database, right? So it is responsible for invalidating the stale data in the front-end clusters. The front-end clusters has Memcache servers, so the authoritative copy, or the database, or the storage cluster in this case, is also responsible for clearing off the stale data. That is very important. So the SQL statements that modify the DB needs to include the Memcache keys that needs to be invalidated. That means whenever someone fires a SQL query to the database, the SQL query needs to be amended in such a way that after the transaction is committed, if it deletes something, then those delete needs to be fanned out to the Memcache cluster so that the stale data is removed as soon as possible. It's not that simple. So that is why they had developed a daemon called MCSQL. So MCSQL is a daemon responsible for inspecting every SQL query, extracting deletes, and broadcasting that whole delete operation to all the Memcache servers. So think about this. There are so many clusters or so many front-end clusters in a region. And if MCSQL is given the responsibility, so it has to go from one cluster to another, and so on, because the Memcache servers are like spread across all the front-end clusters that we have. That is a huge problem because we are talking across cluster boundaries. That will be causing a lot of network choking and stuff like that. So we'll have to optimize how do we invalidate the clusters that we have, so that each front-end cluster has the latest data as soon as possible, and there is not enough load just for doing cross-network communication. The first optimization that they're talking about is reducing packet rates. How do we reduce the packet rates across the cluster boundaries? So MCSQL, instead of sending this data or sending this delete data to the Memcache servers, batches them and sends to MC router. So think about this. We talked about MC router, right? So MC router sits in each of the web server because that's a client. It's a standalone proxy for the the Memcache client, right? So Memcache router sits in that, and it knows what are the available Memcache servers in that cluster, because it will not obviously call to a different cluster, it will call to the same cluster. So it has a right information to know what are the available servers in the same cluster. So once MCSQL fans out the request to the right MC router, the MC router with its data will figure out where the actual request needs to be fanned out to. That is how it will send out to the co-located Memcache servers, reducing, of course, the packet rates. And this is hoping a 18x improvement in performance, because now that they have reduced the cross-cluster communication and they have given the responsibility to MC router, things are much more simple in this case. Let's talk about the optimization 2 that they're talking about. So the optimization 2 is invalidation via web servers. So you might be thinking that, okay, if web servers are getting the delete request, why not give the invalidation responsibility to the web servers instead of the authoritative data source, that is the database or MC squeal, right? The major problem is that it increases the packet overhead, because web servers in general were not meant for batching or sending in compact form. And the second major problem that they faced was due to this. So the web servers provided little recourse, like they didn't have much backup mechanism if things go wrong. So if a misrouting happened due to a configuration error, they had to like restart all of the Memcache server one by one. And that was a huge challenge and expensive. They had to like recreate the database, and that was like a huge challenge. But what MC squeal did is like it maintained a log kind of file. We'll see that diagram probably. So MC squeal could have just replayed the log in this case. Okay, don't have the diagram. Okay. So because MC squeal is getting to execute after each of the SQL transaction. So once that is done, it'll have a maintained log in place. So it'll just replay the log if there is a configuration error, and they have to not be worried about anything else if they have just this set properly. Okay, so let's talk about the regional pools. So how do we minimize the cluster invalidations and stuff, and then talking about the regional pools. So each cluster has an independent memory footprint, because if you think about this, each cluster has a web server, each cluster has, so whenever we refer to cluster here, it's a front-end cluster. Okay, so each cluster will have its web servers, each cluster will have its Memcache servers. So what will happen is they will have a memory footprint based on the request that they're receiving. So if they're kind of receiving skewed requests, then the data that is stored on the cache will be skewed as well. So that is why it is very important to send out uniform traffic across all the clusters, so that in case if one of the clusters go down, we can just replace them with another copy of the same cluster. So that is why it's recommended to mix the data, and that will be easier for us to invalidate, take down for maintenance and all stuff. When we are thinking about this, then there is a problem that comes up because of over replication. So we can reduce the over replication, because now that same data is shared across, there's a problem of memory inefficiencies. We can say that multiple front-end clusters in this case can share the same Memcache servers. That means multiple clusters, like this is one cluster, this is one cluster. The Memcache servers here could be the same thing, and the web servers are connecting to this, and so on. And this is something called as the regional pools. So each region has a pool of Memcached servers, which is called as the regional pools. But it comes back to the square one, right? So we fanned out the MC squeal to MC router just because we didn't want to talk across the cluster. That is the whole problem. So if we do that, then less network bandwidth is available, and again we face the same problem of crossing cluster boundaries. So that is why we have to go via a hybrid approach, where some keys have a single copy or are established in a regional pool, and some keys are replicated across the cluster. And it determines how do we smartly do that. And for that, we use some kind of heuristic to decide which goes where. Do some keys go to the regional cluster, or do some key goes to the replicated one? So these are the primary three things based on which the decision is made. One of them is the access rate. So if it's a lower access rate, we don't mind putting in the regional cluster, because if it is access less, then it don't mind having to require a lot of communication bandwidth between these clusters, right? If the data size is small, then we can say that we can put it in the regional cluster, because if the data size is small, it's consuming probably the wildcard pool of each of these clusters. So if we take it out and then put it in the regional pool, then we can save some percentages of wildcard pool for each of the front end clusters. And then if there are like more unique users accessing the key, then more web servers need to access it. If more web servers need to access it, they need to be present local, and that is how they should be replicated in the cluster itself. And that is how these heuristics are tweaked based on certain requirements to make sure that we have the right balance of replication as well as regional pool. Now it's a very interesting thing. So now that we have talked about different clusters, so it can happen that at certain times one of the cluster failed, right? Or one of the cluster have a requirement that it needs to be replaced. So in that case, a new cluster needs to be installed or provisioned, right? Provision is the right word. So what we can say is, in this case, when we have a new cluster that is provisioned, the cache has no key value pairs because it's just empty. So what will happen is that whenever any web servers are activated, because web servers will be activated in that case, it will be not able to fetch anything from the cache, and all the requests goes to the backend services. And that brings down the whole point of having a cache or adding a new cache layer in the first place, because we added a cache layer just to save the database, reducing the load, but eventually we're increasing the load. So this cold cluster warmup is a strategy to make sure that we are reducing the load on the database, even though we are attaching a new cluster. And how does that work? It's very interesting. So now for cluster warmup, what we can do is we can access the keys from a warm cluster rather than persistent storage. That means if this is a cluster that is new cluster, and if this is a cluster that is existing, let's term this as cold, this is warm because this is being used. So instead of fetching keys from the database to update this cluster, we can fetch from the warm cluster instead and get back the keys and update. So we cut down this call and reduce the load on the backend services, and that is how we'll save a lot of performance or a lot of overload on the backend services of the database. But there is a challenge that comes in. So there's some race condition inconsistency that can happen. So think about this: a old cluster which is warm and a new cluster which is new or cold, we would say, right? So this is the actual database that is residing in the storage cluster being accessed by both of these clusters, and this has Memcache server, this has Memcache servers. So for example, there is a web server here, and this is the Memcache server. This is the web server, this is the Memcache server, right? So this web server fired a delete request for the key K, and this fanned out both of this delete request to this clusters. So this reached first, let's say the delete request reached first, okay? Or probably let's assume that this is an update key, that the web server wrote a new value to the database for key. So the delete request, as usual, should go to both of the cluster because they're not the authoritative source. The storage cluster has the responsibility to make sure that the stale data is taken out of the front-end clusters as soon as possible. So it will fire the delete request. As soon as delete is reached, the Memcache server will evict the value, right? So suppose there is a client or there is another request that comes in, force the web server to access the key K. So it'll try to access the key K in this cluster. It will not be there. So it will try to access it from the warm cluster, right? Because the delete request has not yet received at this point, it will have the older value that is stale, and it will return this to this value, and then the web server will use it. So the main problem is that even if the new value has been updated in the master database, due to a race condition, this value has been stale for some more time, because it can happen that until there is another write request to the database, there will be no delete operation that is getting fired from the authoritative source, and that will keep this value stale for quite some time. And that's a big problem. we need to solve for that. So let's see how the team solved this use case in just a minute. Okay, we discussed the problem. So what did they do is like they implemented a delete with a non-zero hold of time. That means whenever a delete request is sent to a cold cluster, there is a 2-second add hold off. During this time, no new keys can be added to the cluster at this point of time. So what will happen is that, let's go back to the diagram. So in this second, once a delete is fired, it will block any writes. No write is allowed. So this request that is coming in will not be allowed, and will say that, okay, I don't have the data. Even if I have the data, you can't write it. So that will be useless in this case. And whenever the next request comes in, it will try to fetch the key from the warm cluster. And this, in this case, it will have the updated data because it will fetch it from the database and so on and so forth. And then it will have the correct data. So this is a way to say that the race condition can be avoided, or race condition inconsistency can be avoided in this case. Okay, so the warm cluster connection to warm cluster and the cold cluster is shut down as soon as the hit rates stabilizes and there is no more load, or there is no more huge load on the database due to the new cluster that we provision. Okay, so now that we have talked about in cluster, so let's talk about across regions. So now scale this to multiple regions, and how do we see the consistency in there? Okay, so there are several advantages, as you might know, that placing data center in different geographies have different advantages and stuff like that. So some of them are listed here. So it's closer to user, and that is how it reduces the latency. It mitigates the effect of natural disaster because there is very highly unlikely chance that natural disaster happening at all regions that you have established. It can provide some cheaper and power economic alternatives for you to set up the data centers and stuff. So there's a lot of advantages than the disadvantages, of course. Okay, so the major or the primary thing in this case is to maintain the consistency. How do we maintain the consistency of the data across region is a huge challenge. So what will be the setup in this case? So if we have multiple regions, so one region will be the master region. So let's say this represents a region. So each region, the definition of a region says the same. There's multiple front-end clusters sharing a storage cluster that forms a region. So this is a region and this is a master region. So master region will have the master database, and the rest region will have a read-only replicas. That means you cannot write it to the database present in the other regions. So for the writes has to happen to the master database. And MySQL replication is used to keep the replicas in sync across different regions. That is the primary setup we have. So the major challenge is maintaining consistency between the data. Of course, we'll talk about it now. Okay, so let's talk about a situation where we have writes from a master region, right? So we have received the write request from a master region. So the storage cluster that we have is responsible for invalidating data. That is actually an advantage if you talk about it, because if the storage cluster is responsible for invalidating the data, it avoids the race condition that the invalidation comes before the data comes, because as everything is a single source in this case, that will avoid the race condition inconsistency that we have. Had it been web server, it would have been created a lot of problem, because it can happen that the web server gave the invalidation before the data actually came back. So yeah, that is how it goes. So let's talk about writes from a non-master region, right? So consider a case of user, web server handling the user updates the data from a non-master region when the replication lag is very large. So user's request, so it's like is a region 1 and user 2, right? So web server is located here, the master database is located here. the user will write to the master database. And whenever the subsequent request comes in, it will check in the cache and it will see that, oh, there is, oh, sorry, it'll check in the database or in the cache as well that the latest write that this web server did is missing. It's kind of confusing, right? Because these are the read replicas. The read replicas will get the values from the master database. So if the data has not arrived because of the replication lag, nothing can be done in this case. Cache refill should be allowed from a replica's database after the replication lag has been gone. But how could we achieve this? Because if this is not done, then stale data will be fetched from the local database in that region or the read replica, and that will serve the request. It has to be solved in a better way. So let's see how we can solve this. So when we have writes from a non-master region, how do we avoid reading the stale data from the local database or the local read-only replicas of the database that is present in the non-master region? So we'll use something called as remote marker to solve this problem. So let's say we have two different regions. One is a master region and one is a non-master region. So the master region has, of course, web servers, Memcache servers, and a writable database. The non-master region has web servers, Memcache servers, and read-only database. So whenever the web server needs to update or make any writes, so the first thing it has to do is set up a remote marker in this region. That's the first step. And the second step has to go to the master database to write. The third step is that the master replica of the database takes care of the responsibility to fire an RK invalidate statement. That means it has to fire this, and that will be the huge condition to know that whether the database here has local data which is stale or has the corrected data that has arrived, right? Think of this. So if the RK is present, that means the request from the master replica has not yet reached. That means RK is present. That means fetch the correct data from the master database. If RK is not there, that means the request from the master has reached that local database, and whatever value you fetch from the local database is the correct value of the key k. And that is how it solves the stale data problem. So there are still some race condition where, like reading, there is an in-flight read request, but RK is removed, but the database is not yet updated. So what we'll do in that case is just go on in that case to have the stale data, because those are very rare chances. And as per the experiments that are run at Facebook, they have very little chance of existing. Okay, to save bandwidth, in this case, the same channel of communication is used for delete stream as that will of database replication. Okay, so now that we have discussed about the end-to-end system, how do we scale it? Now let's come back to the square one and see some kind of improvements that we can do to make the single server, the single Memcache server more performant, so that it beats the usual open source structure and they have a high performant distributed scale system in place. Okay, so the all-to-all server communication can become a bottleneck as usual. Hence, we did some optimizations. The performance optimizations were that this is a hash table, right? So if you know about the internals of a hash table internally maintains in a linked list or in trees in some cases. Excuse me. So if there are multiple collisions in the same key, the time complexity to search the key becomes linear in time, that is ON, right? So what we can do in this case is automatic expansion of the hash tables to avoid lookup time going to order of n. A whole Memcache server as a server can be made multi-threaded with a global lock. With a global lock, multiple threads can be used to compute all the things that we wanted to do. And then each thread has to be assigned a different UDP, because if each thread is assigned the same UDP, then all the incoming packets through that network communication is handled by a single thread, and it has a lot of context switching overhead because it has to handle everything and a lot more. So if every thread is given an independent UDP port, then this problem is kind of solved in that case. Let's talk about improving the get performance. So instead of using multi-threaded locks that we discussed in the last page, if we use something called as a fine-grained lock. So what is fine-grained lock and what is the difference between the fine-grained lock and a multi-threaded lock? So fine-grained lock is more fine-grained control, is a lock having more fine-grained control, which locks certain part of the data structure. So like instead of locking the whole data structure, it will lock certain part of the data structure to make sure that other parts are accessible, which are not fighting for the same thing. This optimization has been increasing the hits by almost 3 times, because now that they have multi-threaded, now they have included a fine-grained control. Not all of the data structure is logged, so the hits can be more performant, right? And of course, this also increases the misses by 1.67x as well, but the gets are more expensive because it has to compute the results, send back the response and stuff, because the cache misses just send an end in this case. Of course, we discussed using UDP over TCP gives them 13% improvement in the progress. Okay, coming back to the slab allocator. Okay, it's a very interesting topic. Just bear with me. So Memcache uses a slab allocator to manage memory. What does that mean? That means the whole memory is divided into different slab classes, C1, C2, C3, C4, etc. with each of the slab classes having a pre-allocated uniform size memory, which is usually 64 bytes. So whenever it's a hash table, right? And if you remember some scheduling algorithms, there are best fit, worst fit, first fit, and stuff like that. This uses some kind of algorithm to fit the data in the smallest fit slab. That means if a slab is remaining 5 KB and there is another slab having 6 KB and there is a 4 KB of key value that is coming in, it'll stored in the 5 KB instead of 6 KB. So this will be stored here, because in that way they have optimized the performance and stuff like that, right? As we discussed, slab classes start at 64 bytes and increases by 1.7 factor of 1.7 each time till it reaches 1 megabytes. Okay, so each slab maintains a free list of available chunks, and it can request more chunks in 1 MB size once the free list is empty. If they cannot allocate more memory, and that is when they need to evict the items in the cache, and they still use the least recently used algorithm or the strategy to evict items from the cache. So what exactly is the adaptive allocator do? So the adaptive allocator rebalances the slab assignment to match the current workload. Okay, that's kind of a little bit complex. Let's see how it works. So as we have all of the slabs that we had kind of had initial same state because they were assigned a 64 byte of memory in the initial start. So we need to identify the slab classes that are evicting items currently right now. So if they're evicting items, then that means they are the needy classes. They need more spaces, and that is when we term them as the needy classes. If the next item to be evicted from the needy class is 20% more recently used than the average LRU of any other slab, we compute this. So if the item that is evicted next is being used 20% more recently than any of the slab classes that we have, if such a slab class is found, then the slab containing the least recently item used is freed and is transferred to the needy class. That means in this case, the allocator assigns this slab to another class. So that is how adaptive slab allocator improves the performance of the Memcache server. One of the last optimization that they did was the transient item cache. So what exactly is the transient item cache? So if you read a little bit about Memcache, so Memcache supports expiration times. That means you can specify an expiration time beyond which the record should expire. But Memcache implements this in a lazy way. That means the expired items can still live in the memory even after they've expired. So the eviction is lazy the eviction happens by checking the expiration times when serving a GET request. If there is a GET request that comes and they say that, okay, it has expired, then they will evict it, not proactively evicting all of these instances. Because of the lazy eviction, it leads to wastage of memory in certain cases. How do we solve it? So the solution in this case is the hybrid approach of lazy eviction as well as proactively monitoring the short-lived keys. So if you have short-lived keys, we can use some kind of a hybrid approach in this case to do both of this. So short-lived keys are placed in a circular linked list and based on the expression times they have, and then when the times are reached, they're removed. Last but not the least, software upgrades. So software upgrades are kind of thing, it's kind of like a maintenance mode. So if we want to upgrade the software of a Memcache server, we should be able to do it pretty effectively. So as per some stats, Memcache server reaches 90% peak hit rate within few hours. So if we want to do some kind of upgrades, it takes around 12 hours to upgrade a whole Memcache server, as the DB loads needs to be adjusted in this case. So what the team did is, like, the cached values in the Memcache servers are stored in system v shared memory region, which is kind of accessible to multiple processes and all stuff. Because of the sharing ability, one of the instances can be taken off without any disruption, and those can be handled by other servers and stuff. They didn't go about a lot of details into how this thing worked, but this should give you a little bit of understanding of how things should be in this case. Okay, finally, we are at the conclusion of a huge video learning so many lessons. So the first lesson is separating cache and the persistent storage allows us to scale things independently, because that's what they did. We have a MySQL layer, we have a cache layer, so we did separate out both of the things, and that helped us allow to scale our things independently. Monitoring, debugging, operational efficiencies are as much important as the performance of the application. Very true. And of course, managing stateful components is operationally more complex than managing the stateless ones, and that is why we did go into the Memcache client, which is stateless, and we could go with multiple quick iterations, quick deployments and stuff. Is roll out. Like, we should be able to roll out a feature one by one like that. And there should be a support of immediate rollback of a new feature. If things go wrong, we should be able to roll back that feature as soon as possible with the least amount of disruption. And of course, simplicity is vital. So we have to build systems so that simplicity is at the center of the design, and that is how it will work out. All right, that's all I have for today, guys. I hope you liked the videos, like the little intricacies that we had while building a system from a single machine to a distributed system that's scaled across different regions, across multiple geographies. Let me know in the comment section if you have any questions. I will link all the papers and documents in the description, and see you in the next one. Thank you.